All right. Hello, everyone. Welcome to a machine learning interview question. This question is going to be focused on linear regression and is likely to be asked in applied scientist or research scientist positions, as well as data scientist positions, but is also possibly asked in machine learning engineer positions. Now, again, a lot of these positions vary company to company. So regardless of whether you're applying to any of these four or others that touch upon ML, this is a very good question to know because it is very common and it is relatively straightforward. So it is very popular. So first thing we're going to do is we're going to define the problem statement, and then I'm going to walk you through how to break down the solution step by step, along with some follow-up questions. So first, very, very simple problem statement. Explain how linear regression works and then create a working example. So sometimes you'll have people ask you just how to explain how linear regression works, but not actually create any kind of code, or we'll ask you to do pseudocode. Now, coding or pseudocoding is relatively not, that much of a difference. If you know how to code it, you can do pseudocoding. But if you only know how to pseudocode, that's not as good because you want to be able to write the actual code if needed. So we're going to walk through how to write the actual code. And if they only ask for pseudocode, you can do that very easily. All right, so the solution here. We're going to go through some basic assumptions. The first thing they're going to ask is, what is linear regression and what are the four basic assumptions? So you should know this. These are, one, linearity. So the relationship between X, the data, and Y, the answer, is linear. So that is almost too obvious, right? It's linear regression. It has to be linear. It's not quadratic regression. Next, homoscedasticity. So the variance of the residual is evenly distributed throughout all values of X. So this is very important because say as X increases, so does the variance of your residuals. We're going to call that a fanning effect. So towards lower values of X, you have very small residuals. Towards higher values of X, you have big residuals, both up and down. That could mean that a linear regression may not be the right fit for your data, or that there's something underlying about your data that you need to pre-process or scale for it to work well with linear regression. Secondly, residuals can start all very positive over low values of X, then get very negative over medium values of X, and again, be very positive over high value of X. So that's going to be like a U shape on top of a line. That is an indication that your data is not linear. And so homoscedasticity is that assumption that verifies that. Independence, spelled that wrong right there, but you know what that means. The observations are independent. So this is true of almost all types of machine learning. There are going to be exceptions, but generally speaking, all linear regressions, observations in a linear regression should be independent. And then normality. For any fixed value of X, Y is normally distributed. So that's pretty self-explanatory. So these are the four basic assumptions of linear regression. If you have any questions, feel free to reach out to the operations team or anyone else. The instructors such as myself will be happy to answer that, but these should be burned into your brain. So next, we want to explain when and when not to use linear regression. So when to use, right? When is it convenient? When is it correct? It is easy and it is simple to train and implement. Linear regression is generally the first algorithm you're taught in most schools of machine learning or even statistics, and can be very easy to get a proof of concept going. Next, it's a very fast learning algorithm. It can be done either with gradient descent or one shot. So one shot is, if you're not familiar, just a way to do some matrix math based on the input data vector and the input y vector. So once you have both of those, you can just calculate the weight vector without any kind of gradient descent. Now, that has its limitations as well, but it can also be very, very quick. So lastly, it handles linear data very well. It's one of the best and simplest models to just go ahead and make a linear fit in linear data. So if you have linear data, you know that's the case, then fantastic. Try linear regression first. When not to use, linear data is not linear. So again, self-explanatory. you might need some extra time for pre-processing or feature engineering. So linear regression, because it is a simple algorithm and it has a lot of assumptions, a lot of the time you may need to fit your data into those assumptions. That could mean normal scaling your data or your features before they go into training. So other algorithms, depending on the algorithm, may not need as much feature engineering, but linear regression, that might be the cost for the simplicity of it, just getting it up and running. It's prone to overfitting, and it is also noise sensitive. So both of those things can be an issue. Again, that's just up to you to understand the type of data you're working with, have some domain knowledge, and use wisdom. All right, now step 3 is going to be to define the equations. Let's do just that. So what's the equation of a line, slope-intercept form? Y equals mx plus b. So everyone learned that maybe in middle school or the equivalent. This is a very, very simple way of describing a line. Now, linear regression is the exact same. And all we're going to need to do is just define that in terms that are more standard for machine learning or academia. So that is y equals b naught or beta naught plus beta 1 x1, beta 2 x2 plus ... all the way to beta n xn. So beta naught or beta 0 is the intercept, and everything else, all the betas, are the weights, and x is going to be that value of that feature for that observation. Once you add all of those up, you get the prediction for y. So that's exactly what we defined here. And now we're going to make a plan on how to solve this question when someone says, let's code it up. So again, just want to reiterate, a lot of the time you might be doing this on a whiteboard and just need to do pseudocode, which it'll be a lot easier. But if you need to write actual code, I'm going to show you how to do that without the use of any third-party library so that you can be as familiar with the basic Python data structures. Now, if you want to use NumPy or something like that on top of this data or on top of this solution, that is a bonus, can make your code a little bit more efficient. And that's something I encourage you to explore with and understand on your own. Okay, so what we're actually going to do here is dive into the pseudocode a bit, just for the sake of clarity. Sometimes it can be a little bit tough to translate from the code to pseudocode or back. So I'm going to make sure that we cover both of them instead. So let's go about what this pseudocode would look like if we were given the example that we've gone through so far. So here we wrote a plan that says define how to initialize our linear regression, define a fit, and define a predict function. So let's do exactly that. Do an initialize model. And here what we're going to do is we're going to define init. We're going to pretend this is like sort of Python-y pseudocode, but you can do it in however you want. So first, we need to define the hyperparameters. This is where the user will input in the hyperparameters, and we're just going to define what type they would be and maybe a default value or something like that. So first we'll have the learning rate. This is going to be a float, and a default could be something normal like 0.5 or 1. Let's call it 1. Okay. Next, we have our training iterations. Gradient descent. So this is how many times in our training loop that we update the parameters. So again, this is a hyperparameter. This is going to be an integer, and we can say default equals 100. Lastly, we want to have a trained flag. It's trained, and it's going to be a Boolean, and it's going to be set to false. So this is how we know that if we're going to use the model that we initialized to predict something, that it's actually been trained rather than, it's just a initialized model that we're hoping will work. So there we go. The init part is very simple. So now this is the part that is kind of the meat of what the interviewer is going to be asking for. Training function, or in this case, we're going to call it the fit function. So here we're saying define fit. In fit, we're going to take in 2 parameters. We're going to have x, which is going to be our data. It's going to be a matrix of floats, and y, which is going to be a vector / array, and it's not going to have any output. So now, what do we do first? First, we want to do input validation. So we need to make sure x and y are the same size in terms of how many examples there are. So that's something that is not necessarily super important to mention during interview, but it takes 2 seconds and shows the interviewer that you're really thinking about the problem, so might as well. Next, we're going to have a function, we're going to initialize learn parameters. Okay, so these are going to be intercept random slope values for each feature. So here, above, we talked about y equals mx plus b, or y equals b naught plus b1 all the way to bn. This is just those parameters, the b's that we're learning. And one thing to note is this can be its own function. Okay. Next, we want to start our training loop. Right? So this is where each of these values comes into play. So training iterations for gradient descent. So if we have 100 value here, it's going to go through this loop 100 times. And we're going to say for each iteration, we're going to do the following. We're going to, 1, calculate the gradient of intercept and slope values. So this can be its own function right here. Next, what we're going to do is we're going to increment slope and intercept values with gradients and learning rate. This is where the learning rate comes into play, right? And the gradients and our current values. So this is going to be a little bit of logic. So this also can be its function. Next, we're going to just repeat this until iterations are over. So assuming we've done that, now what we need to do is just save the final parameters of slope and intercept. And then we will set switch model is train flag from false to true. Awesome. Okay, now that's really as simple as our fit function needs to be. We can always expand upon certain parts of it later, but that's the general part, what someone is looking for. So here now, what we're going to do is we're going to do our prediction. Okay, so we're going to define predict. So we're trying to keep it kind of similar to how scikit-learn would do it with fit and predict. Of course, you can use any kind of names you want, but these are just generally pretty familiar. So now we're going to define predict. Predict is going to take an x test, let's just call it that, and this is also going to be a matrix. It's also going to output a vector of, or prediction vector, let's call it that. Okay. How does the predict function work here? So first, what we want to do is validate that x has the same number of features as our slope vector. So that dimension of those vectors needs to be aligned, right? We need to have as many x values up here as the b1 through n. So if that's the case, then the data is the right size and we can keep going. We also need to validate that the model is trained flag equals true. So if it's not trained, then we cannot predict. Okay. Now, there are 2 ways to kind of go about this. We can define the simple way. So this is going to say for each observation in X test, we're going to predict an output value. And how do we do that? All we do is we do the feature vector times the weight vector plus the intercept. So again, y equals mx plus b, where here m and x, or the b vector, beta vector, and the weight vector sorry, the weight vector being the b vector, beta vector, and the feature vector being all the x's, right? These can be vectors, and this is just a single number. So you multiply these pairwise, and you have this. Okay. And then you can append them to a list and output the final guesses of predictions, let's call it that. Okay. There's also the efficient way. So this is what we're going to say is context dependent, right? So I'm using the most basic data types in this pseudocode. A matrix is just going to be a list of lists, and a prediction vector is going to be a list of numbers. In theory, depending on the library or the position you're interviewing for, the library you're using, you have more options. You can use NumPy if you're using Python. You can use data frames if you're using R. You can do other stuff in Stata. It really just depends. But if you are comfortable with whichever language you're using and a specific library to do these kind of calculations, you can say, we can use NumPy or another matrix optimized library to predict over data frame at once. Cool. So that's where you would just have, NumPy pairwise and operators, stuff like that. And this really does it for the pseudocode. This is all it needs to be, especially when you're interviewing. Sometimes the interviewer may ask you to dive more deeply into each of these, but those are going to be pretty context dependent, right? So calculating the gradient of the intercept and slope values, and that's just going to depend on the specific model you're using, incrementing the slope and intercept values with gradients and learning rate, right? That's going to be relatively straightforward, but usually if you're asked to do pseudocode, you may need to translate that into real code. And that's not always the case. Sometimes they just ask you to write pseudocode and that's it. But especially with online interviews, you're going to be required most of the time to write some kind of functioning code. So what we're going to do after this is we're going to take this pseudocode, translate it into real code, and then pass in some test data to compare with actual scikit-learn in Python and our model and see how much they differ.